Morning, good afternoon, good evening, wherever you're joining us from. Welcome to the first CODA webinar of 2026, and I think we're starting off with an absolute cracker here. I am so excited with both the topic and the presenter that we have for this session to start the year. So I would really like to welcome James Vickery, who is from Process Mercury Group. Coming to us from Ecuador, which really is, it's a remarkable recognition, I guess, of the diversity and spread of the industry that we work in. And James is going to go through process mercury management during oil and gas decommissioning. So I will hand over to you, James, to take it from here, please.
Thank you for that introduction, Francis. I'm going to jump right in and thank everybody for joining. And I'm going to start out with a bit of my own personal history to give you an idea of how I ended up in this business. It all started back in 1957. This photo you see is a gas plant construction site on the Mississippi River in Louisiana, and my father, the plant owner, and my father's engineer. And just to tell you, I grew up in this family business of oil and gas construction. So as soon as I was old enough to handle a pipe wrench or a shovel, we were working in the summers on my father's construction crews. And that continued pretty much through the 60s, 70s, and 80s. And then in 1969, I escaped the family business for several years. I joined the Texas Maritime Academy and pursued a degree in marine engineering. And I shipped out for several years on this old rust bucket called the Texas Clipper, which is a World War II converted troop carrier. I rejoined the family business in the 80s and worked until we sold the business in the late 80s. And then I went to Core Laboratories, which is an analytical geology laboratory that supports the oil and gas exploration industry. In 1994, I joined a shipbreaker scrapyard company with several shipbreaking and scrapyards along the Gulf of Mexico and Texas, Louisiana, Mississippi, Alabama, and Florida. I was with them for several years, and then I joined a national environmental consulting company to join their group specializing in the oil and gas industry. In 2005 is where we started. We got our first Mercury project, a major natural gas processing and transmission company in North America, came to the company I was working for, looking for some natural gas expertise, and the environmental manager of that gas transmission company, who is now on our staff, Mark Nelson's name, put together a team with Dr. Mark Nelson, myself, and him to begin to assess and manage their mercury issues. In 2014, Patrick Lane and Jason Buellman and myself formed the Process Mercury Group. I mentioned this first project that we got. It was in the Gulf of Mexico with a complex of platforms in a gas field that had some very high concentrations of mercury in the gas. As you'll see, I've got a couple of data points on here. Here at the production platform with the highest concentrations, it was 650 micrograms to 1,000 micrograms per standard cubic meter. There it goes into a 10-mile subsea pipeline, and you can see that we knew that we were losing mercury to the subsea pipeline. The concentrations were reduced by half. There it goes into a gas collection and junction platform, and there the gas is transported to a dehydration station. Again, we see another drop. This is 40 miles of large diameter subsea pipe. Again, we knew we were losing mercury to these gas pipelines. The extent of this contamination extended to a major gas transmission pipeline and I've listed a couple of the sludge numbers here. This one here is approximately 200 miles downstream from the platform. The sludge in the pigging waste, pigging sludge was 1.9% was the concentration of mercury. Here we're another 100 miles downstream. Still, we're in some samples we're getting 1%, and here we're another 300 miles downstream and still at 300 milligrams per kilogram. And all of this, it becomes hazardous waste. So the client was very keen on working out the issues with this. With decommit, this I want to give you all kind of our point of view and our approach, and it may be common, but two central questions arise when you're considering a decommissioning a mercury impacted facility, and that is always, what are the regulatory requirements? Like, how clean is clean? And the way we approach that is we look at the applicable and relevant and appropriate requirements. We'll be able to look at all the range of those and develop a regulatory pathway. And typically the two options for decommissioning facilities are leave it in situ if it's low enough mercury concentrations, or remove it and recycle it. And each one of these comes with its own particular residual mercury limits. And when you've sorted that out, you have a good handle on your decontamination requirements. The other central question is, okay, how much mercury and where is it? We always start, all of the projects that we worked in start at some point with some process knowledge. And what I mean by that is this could be observational, like for the project I'm talking to you about today, the crew that was handling the pigging operations at one of their pigging receivers, they noticed mercury beads on the pigs. I'll have a picture of that a little bit later. But that started the project. We looked that they notified us, then we began to identify what data is available. We gathered up our data gaps and put together an assessment program to implement a mercury mapping and mass loading and distribution program. And this told us what are the levels of mercury and where is the mercury. So then with that data, we began to evaluate decontamination technologies, what's feasible, and then we're able to put that together into a decontamination plan. Just another look here. These were the major impacted portions of the impacted facilities. These had the highest concentrations. This area over here to the left is the offshore platforms, the two connecting pipelines. This area right here is a separation and dehydration station handling about 750 million cubic feet a day of natural gas. And it was separated into rich gas, which was routed to a local cryogenic processing plant, and the balance was put into the gas transmission interconnect. This is the result of our mercury mass mapping project. As you can see, we divided it up into three segments. Segment one was where the mercury is produced. We were over a period, we monitored the facility over a period of 6 years. We monitored the mercury in the gas, in the condensate that was produced, in the salt water, the produced water that was produced, and we did an assessment of surface mercury on the process wetted surfaces on the offshore platforms and subsea pipelines, as well as on the impacted portion of the onshore pipelines. We also followed the mercury through partitioning to the produced water, what was partitioned and delivered into the dry gas transmission lines, what was partitioned and delivered to the cryogenic plant, what ended up in solid waste to disposal, and what was in the condensate that went to cells. You can see there's some 1.7, almost 1.8 tons went out into the gas the gas transmission pipe. A good bit went into the cryogenic plant, and 3 tons went into the condensate to sales. And speaking of surface mercury that was in the subsea pipelines in particular, we selected some sections of pipe in each one of the impacted segments, and we cold cut sections of pipe out, cut it into cans, cut it into rings, and ultimately ended up with some coupons that we digested and determined the mercury concentration in each one of these. And what we found out, and this has kind of been collaborated over several years since then, that depending on flow dynamics, the mercury tends to accumulate more on the bottom half of the pipe. Here you can see some pretty high concentrations, 58 grams per square meter. Here it's almost 10 grams per square meter. Up higher in the pipe, it tends to be less. And speaking of XRF and surface mercury, we developed some detailed work instructions for an assessment project in Australia. This is the table of contents for that work instruction. And the reason we did this was to give the technicians that were handling the XRF analyzers real detailed instruction, because we had a certain data quality objectives that we wanted to achieve. And typically XRF was considered to be more of a screening tool, but we worked with the manufacturer of the XRF, and we developed a means and protocol for producing what we consider to be compliance quality data. And this is a mercury mapping and verification protocol, again, for another Australian operator. Again, this is a detailed sampling analysis plan based on XRF for a facility that had an extensive amount of process wetted surface area that was mercury impacted. And our goal here was to produce compliance quality data that could be used to verify to the environmental agency or to buyers or to scrap recyclers that we have done an accurate and representative job of assessing the mercury. When I talk about compliance data quality, this is an example of a project and the data quality objectives. This RSML, this is the residual surface mercury limit that we were working with. It was, for this project, it was 20 micrograms per square centimeter. We wanted to achieve an accuracy of plus or minus 10% and a precision acceptance criteria of 20% relative percent difference. For representativeness, it was so extensive that we decided our objective would be to assess 5% of the impacted surface area. And completeness speaks to just collection of the data and all of the details of the data collection process. These projects tend to produce a lot of scrap steel and high quality scrap steel, what's typically referred to as heavy melt scrap or plate and structural scrap. It's valuable product, sometimes $250, $300 USD per ton. This is a recycling protocol based on local regulations for a particular jurisdiction and the electric arc furnaces acceptance criteria. And there essentially are 4 acceptance criteria here: that there can't be any sludge or any sludge-bound mercury present when it's delivered to the recycler. In this case, the wall-bound mercury limit was 20 milligrams per kilogram. That's a mass limit. And the third criteria was that there can't be any liquid phase mercury in the steel. Here we used a vapor standard of 6 micrograms per cubic meter. This is a US EPA criteria for assessing enclosed spaces for liquid mercury. If you have greater than 6 micrograms, it's an indicator that somewhere in the enclosed space there's liquid mercury. The final criteria was that the scrap steel had to be cut to meet the metal charge size requirements, essentially the dimensional limits of the electric arc furnace's furnace. This is an example of a mercury impacted pipe management guide that we prepared for our gas transmission client. In 2017, they entered into a major reconstruction project of several hundred miles of large diameter pipe. They were reverse flowing, they were replacing pipe, they were doing major maintenance. And this was in an area that had a lot of mercury impact, historical mercury impact. So there was a lot of pipe that had to be removed and recycled, and a considerable amount that had to be abandoned in place. And this was the manual that we developed, the manual guide that we developed for their engineers that were overseeing that project. And we talk about decontamination, and chemical decontamination is a popular approach. It comes with its own advantages and disadvantages. This is an example back in 2022-23. We did an evaluation of 7 chemicals, again, for an Australian operator. And as you can see, this was a blind study. We didn't know anything about the chemicals. They were all treated the same way. And as you can see, some of the chemicals didn't do anything at all. Some of them did have some reduction capability, and some of them worked quite well and worked quite quickly. But we urge anyone who's considering doing a chemical decontamination process or project to evaluate the chemicals. But because each project is unique, and the depositional characteristics of mercury vary with the type of production and geology that the mercury comes with. And health and safety and occupational exposure are always a concern when decommissioning mercury impacted facilities, especially hot work. And over the last couple of years, we've done some pilot scale studies, continually monitoring mercury in the breathing zone during hot work activities. And what we found was quite surprising. And the surprise was that even when surface mercury concentrations, when measured with XRF, concentrations as low as 1 or 2 micrograms per square centimeter, when they're hit with a welding arc or a acetylene torch, can produce breathing zone mercury concentrations that exceed the acceptable limits, that exceed the OSHA permissible limit, which is 100 micrograms per cubic meter. And this is an example of a project that we completed back in 2024. It was a mercury contaminated demethanizer that needed to be decontaminated and needed to have the separation trays modified. So there was a lot of hot work, a lot of cutting, grinding in the modification process, and we were able to continually monitor the mercury concentration in the welder's breathing zone. And here you can see the spikes of the welding process over an order of magnitude over the OSHA ceiling limit. So this just supports, and we knew that through our own measurements, we knew that the mercury surface concentrations were very low. So this just gives you an idea of what can happen. And we do have some Australian project experience. I've mentioned a bit of it. We've done quite a bit of work for a mercury impacted offshore gas production facility, including an FSO. We produced a mercury management manual for an LNG facility in Australia. we planned and provided the oversight of an atmospheric mercury deposition project. And through our partnership with HRL, we're now providing mercury and gas measurement and monitoring services. And I'm going to go through just a couple of 2 or 3 slides here to give you an idea of some of the research and development that we're working on. This is what we call a dry decon system. It's based on using a inductive heating unit. This is what here we call the thermal source. The reason for us considering and beginning to work on this is to provide an alternative to the chemical cleaning process, which has its problems with waste management. This is a means of, and of course it has to be ex situ. It means the pipe has to be taken out and taken on shore. And this worked quite well, but essentially the mercury is thoroughly desorbed in the pipe. We do a nitrogen flush. It flushes the nitrogen out with the flushes the mercury out with the nitrogen. Then we run it through a mercury absorber. And here in this one, we recycle the clean nitrogen through. This is what it looks like in the field. This is just our field pilot unit. This is the inductive coupled inductive heating unit. Here you see it. We've got a pipe can mounted on a pipe roller, and we're rolling the pipe and heating the surface with the inductive heating unit. And we were able to increase the temperatures to 600 degrees C in a pretty quick process, and it worked very well. And this is what we call the Mercury Rat. It's a robotic assessment tool with a portable XRF analyzer mounted on it. The tracks are magnetic, and the idea here is that we can reach areas that are difficult to access and take mercury measurements in those areas. And in partnership with Chevron, we evaluated prompt gamma activation analysis as a means for determining the surface mercury concentration on the inside of the pipe without cutting the pipe or getting inside of the pipe. We did this, I think this was back in 2022, and this is a published paper. Just wanted to talk a little bit about our team. Patrick Lane is our managing director. Jason Buellman, our director of operations. Both of them have almost 20 years of experience. The 3 of us have been working together for almost 20 years. You know me, I go by Vic. I'm the technical director. Mark Nelson is our gas gathering and transmission subject matter expert with 30 years of experience. And Glenn Ebert, who's located in Bangkok, is our mercury and norm decontamination SME. Our long-standing clients that we've been working with for almost 20 years now, Chevron, Williams, and Axons. We've done a lot of work with them and are happy to have been working for them. And I'm glad to take any questions now. I appreciate everybody's time in putting this together.
That's been absolutely fascinating. Thank you very much, Vic. We haven't had anybody put any questions into the chat yet, but that's not unusual. Normally it takes a couple of minutes for people just to get their questions formulated, and then we end up getting flooded with them, which is more or less what I'm expecting here. Maybe a couple from me just to get things warmed up.
Okay.
When you look at the decommissioning side of the industry, specifically, where do you see the biggest challenges from a mercury perspective?
And I think it's, the first thing that comes to mind is mercury impacted subsea pipe. And I know there's a good bit in Australia. Of course, the Gulf of Mexico is a big spaghetti bowl. Not most of it is not mercury impacted, but there is. We have dealt with a number of subsea pipes that were mercury impacted, and we have successfully decommissioned a couple of large diameter pipes. And it's problematic. It takes a long time. There are a lot of stakeholders in the process, and the regulatory environment is fluid. And those those are challenges that I see. And
Yeah. Yep. No, that's certainly a big area of a big topic of discussion here is contaminated pipelines, those subsea ones in particular.
I'm sure it is.
So yeah. So we have our first question, and that's coming from Sean. Many of you will know Sean, our former GM. So he's always quick to get in with a question.
Thank you,
it's a cracker, actually. Yeah, thanks, Sean. So he's asking, what is the technology readiness level for the system that you showed in one of your last slides, that nitrogen-based mercury removal system?
Oh, yeah. So that one.
That one. That one. Yeah.
This reply.
Yeah.
No, I see it. Yeah. So we put this together. We put the pilot scale system together. My partner Patrick has done some work, and we haven't fielded a full-scale version of this yet. We're capable of fielding a full-scale version in about 6 months, and so that's where we're at. And it's really we took some of this technology off the shelf that had another application. So, but upon demand, there has to be some development for different pipe diameters. So I would say if somebody came to us and said, hey, we've got 1,000 joints of 6-inch or 8-inch or 14-inch pipe, we could be ready in 6 months.
Excellent. So as I suspected, the questions are starting to flow in now. So I'll try and do my best to take them in order, or link them if that's the case as well. So Brian's on the same technology there. Brian's asking if you could talk about how coatings may or may not hinder that nitrogen-based removal system from pipelines. Coatings, yeah.
Yeah. We haven't worked with this technology on coating with internal coatings. You're talking about internal coatings? Awesome. And yeah, we haven't worked with internal coatings yet. We'd need to do a pilot scale assessment of that before we move to a full scale.
Yep. Very good. No, that's great. Thank you very much. Next one from Darren, who we all know over here as a big deep thinker in the mercury space as well. So I expected to see you on, Darren, and not surprised to see questions coming from you as well. So Darren's question: do you have any suggestions for how operators can characterize the mercury inventories for subsea pipelines without destructive sampling? And then an example was prompt gamma activation analysis, feasible technique.
Yeah. So that's why we assess the capability of prompt gamma activation analysis. And really one of the things that drove us to begin to assess the feasibility of prompt gamma is that there are some portable neutron generators on the market nowadays. Okay. And they're electronic, and they don't have a radioactive source. So they're on off. So when it's off, there's no radioactivity. When it's on, it's generating a neutron beam, a neutron flux. We did some initial trials with the portable neutron generator, and we stopped the project because we ran out of money, essentially, because we needed to do some extensive modeling to work out the
And
Uh, we had to thermalize. One of the things is that we use different materials to for shielding and different materials for thermalizing the neutron flux. And what we realized is that we needed to do some modeling to move that technology forward. And we didn't have the money at the time, and we had some other projects that we needed to get onto. So that's where we left it. The other approach is that if an operator realizes early in the life of the facility that they have mercury, a mercury monitoring program can really, in strategic sampling points, can give you an idea of how much mercury is accumulating in the different sections of the facility. And what you can begin to make some assumptions and use some models to develop some, and that's what we've done based on the data that we gathered from actual decontamination, actual digestion of coupons. We use those to make assumptions, some mercury deposition assumptions, mercury deposition rate assumptions. So that's kind of my thoughts on that.
Very good. Thank you. Okay, the questions are coming in thick and fast here now. So next one on the list, what sorts of discussions are you having with regulators? And I imagine the regulations and regulators everywhere you work will be different, or subtly different at least.
Yeah. Well, of course, the conversations vary according to country and jurisdiction. Recently, I've been focused on the regulations around mercury impacted scrap pipe. Okay, and this of course is downstream from the decommissioning. Once the pipes out of the facility, I've just completed an evaluation of 14 countries' regulations with regards to the recycling of mercury impacted steel in general, pipe, heavy melt steel, as well as plate and structural, but all mercury impacted. And there's some similarities across the particular 14 countries that we looked at, but there is variation as well. And of course, Minamata is since they've come out a year or so ago with their mercury waste, numerical mercury waste criteria, that's entering into the discussion now that the Basel Convention has come out and decided that they're going to harmonize their regulatory language with the Minamata mercury waste criteria. That's entering into the conversation as well. And that's kind of my initial thoughts on that question.
Very good, thank you. I just want to go back to Brian's question, because I think I maybe phrased it wrong. This was around the coatings with how coatings could hinder the nitrogen-based mercury removal. It was actually, he was looking at external coatings, I believe.
Yeah. So
in the way that was.
So
yeah.
Yeah. So this inductive heating unit will remove the external coat and so what that does with external coating is that you've got to be ready to handle the waste that's generated from that. But it's not going to impact the removal of mercury from the internal mercury impacted surfaces.
And I think I understand that. If Brian's obviously still on the call, if you've got a follow up on that one, Brian, then please feel free to put it in, and we'll come back around on that one. So next one here, where are we? Have you investigated putting an XRF on a pig to assess pipeline mercury contamination levels? I've heard this talked about as by a few folks over the years. Wouldn't it be nice if we had one of these? Is this something that you've looked at? Or aware of others looking at, maybe?
No, we're aware of other other groups that have considered that and actually done some preliminary work, but that we haven't done any of that.
And very good, thank you.
I tell you, our experience with pigging is that it's risky. A number of times back in the day when I was working in the oil fields construction industry, I was on some pigging projects, and pigs get stuck, pigs get damaged. It's to put a $40,000 instrument on a pig. Well, you have to have characterized that pipe run really well and be confident that there are no anomalies in that pipe run. So
you want your $40,000 investment to come out the other end of the pipe in the same condition you put it in as best as possible. Eh?
Yeah, that's always a happy ending. Yeah.
Yes. Okay, next one here. What about the acceptable limit, UCL, of surface-bound mercury, often mentioned as 20 micrograms per square centimeter?
I'm sorry, I don't really understand the question.
No, I'm not sure there's a full question in there, but maybe let's just say maybe it's how achievable it may be, or if I put my view on that, how achievable, how easy is it to get to that 20 micrograms per square centimeter from a surface bound mercury level when you clean it?
Well, there's considerations that go into that. If you've got the pipe, I'm assuming it's a pipe. If you've got it ex situ, meaning that you've got it out of service and you've got it, if it's not 300 meters below sea level in the ocean, it's a lot easier. Okay, if you're working on subsea pipe at 300 meters, and it's of course the conditions are more difficult, but if you're just, I don't know how to characterize or quantify easy. It's achievable. Okay, of course it depends on where you're starting. If you're starting from 1,000 micrograms per square centimeter, or if you're starting from 50 micrograms per square centimeter. But for example, with this thermal approach, when you kick the temperature up to 600 degrees centigrade, any type of mercury in there is going to vaporize, and you can flush it out with the nitrogen. That is highly achievable. You can do it with mineral acids as well. You can do it with other chemical approaches as well. It's just how aggressive you have to be, and how prepared you are to handle, in the case of chemical process decontamination processes, you got to be prepared to handle high concentration acidic or basic waste. Those are kind of some of the issues associated with that, but it's achievable.
Very good. And having just mentioned waste in there, next question we have here. What do you do with any mercury impacted GAC in the mercury capture cleaning process?
Yeah, the granulated activated carbon with sulfur. There's a couple of pathways for waste management on that. But typically what we would do is we would go to a hazardous waste landfill. And it's a reduced volume. It's not acidic. However, it would have high concentrations of mercury.
Yep. It'll be properly managed. A couple of questions that are quite similar here, so I'm going to assume that they are more or less the same question. Are you able to share the study that you talked about regarding scrap steel limits by country? Is that something that you have that could be made available?
Well,
Yeah.
that was done under contract.
Yep.
So it's a deliverable product, and it's not publicly available.
Fair enough.
Of course, you know, I'm available our company is available on a consulting basis to help
Yep.
anyone who needs to work on that aspect.
Yep. Nope. Fair point. Fair point. Yep. Someone's paid for that work, and quite right. So, um, okay, where are we now? So we've got one here to follow up from somebody. So from Santh's question above, what percentage of the hydrogen present within the pipe can be expected to be removed by a nitrogen flushing? Your nitrogen flushing flow circuit has got a lot of interest.
Yeah, I know that. I figured it
Yeah.
would. So what our objective was to just do one pass. Okay.
Mhm.
Take a length of pipe. It's 10 meters or what. Take a length of pipe, run it through in the design, the inductive heating unit is circular and is clamped around the pipe so that it's heated in the total circumference simultaneously. So our objective was just to make one pass. And we removed in our test case, in our pilot scale test case, we removed 95% of the mercury on one pass. If 95% wasn't sufficient, you can do another pass. Now, this does take quite a bit of electricity. So that's a resource and cost consideration, but it's a highly effective approach.
Very good. We're almost at the end, Vic. Well, we are until people put the next bunch of questions in. So, yeah. Okay, we had two. Now we've got three questions left. Right, here we go. So this is quite a long one here. So essentially, you mentioned you got to a point in conjunction with the XRF manufacturer that XRF could achieve low enough limits of detection to determine that steel is compliant. The question goes on, could you elaborate on how this can be, seeing as the XRF cannot account for the thickness of internal scales, but it's only a surface measurement? I guess, how do you see below the surface with your XRF to get the numbers?
Yeah, there are ways to approach that, and I expect that the questioner knows this. So there's a couple approaches to this. Okay. If you're entering into a project where you want to use XRF to generate compliance quality data, and you're unaware, there are a couple of approaches you can use. You can use X-ray diffraction. There's a couple of approaches you can use to characterize the thickness of the scale. Okay. Of course, this requires collecting coupons and getting them ex situ and taking them to a laboratory that's capable of doing XRD, and you can characterize the scale thickness. There's a couple of other analytical approaches to characterizing scale thickness, and I know we know that there is a limit to the depth of penetration of XRF. The other way, you can do acid digestion on the coupons. Once you characterize the scale depth, you can do some acid digestion on the coupons. You're going to remove all the scale, determine all the mercury concentration in the scale, and then use that to, so to speak, calibrate your XRF, or put a calibration factor on your XRF.
Yep.
And
Very good. Right. Now, in the interest of trying to finish by past, I will ask the questions that are in now, and then we'll draw a line at that point. So we've got 4 questions left, Vic. So here we go. What exact part of infrastructure was the 650 micrograms per centimeter reading taken from on the project that you were working on, e.g., pipeline, XT, so Christmas tree, wellhead? I guess where in the system did you see that?
So that was that. I think what the questioner is referring to is and and is this 650 micrograms per standard cubic meter.
Yep.
Is that right? That was a measurement in natural gas. Is that correct?
It must be. Yeah, that must be the. All right. So that was in the gas, right?
Yeah, that was in the gas, and that was at the inlet to the gas gathering lateral that was serving that production platform. And
very good. Thank you. Yeah, that's someone with a good memory to know to go back that far through the numbers. Okay, the limit of 20 micrograms was given for FPSO decontamination, tanks and topsides. Our industry requires a rule like, for example, to be mentioned EU number 1257/2013. I assume that means, I hope that means something to you.
I'm assuming that's a European Union
yes, yeah.
criteria.
Yeah.
And what was the rest of that question?
So, reading it verbatim, the limit of 20 micrograms per square centimeter was given for FPSO decontamination, tanks and topside. Mm-hmm. Our industry requires a rule, for example, to be mentioned EU number. So I'm assuming, and I'm not familiar with this EU.
Yeah. So that was a specific case. That 20 micrograms per square centimeter was a specific case that was probably 2026. That's probably 5 or 6 years old now. And then I think that, sorry, my dog's barking. I think that now, I'm not extremely familiar with the EU regulations around these decontamination levels, these residual mercury levels. But I think that the Minamata mercury waste categories, their numerical limits as well, is going to have an impact on this discussion. And
very good. So two left, Vic, and then you can go and see what your dog's after you for.
Okay.
So next one here. Thanks for the presentation. Was wondering, on site-based onshore or offshore decontamination, do you see a place or need for temporary water treatment plant for any contaminated cleaning water or chemical streams used? If so, have you any idea of typical volumes of feed water used during flushing or cleaning programs?
So is this question related to chemical decontamination?
I would say this is chemical. Yeah, this is going to be basically water-based decontamination, I would suggest.
Right. And the question is about volumes of.
Yeah. If so, do you have any ideas of typical volumes of feed water used during flushing or cleaning programs?
Okay. I think when designing a chemical decontamination program, the amount of water, the amount of feed water that you're going to use is really going to depend on the pipe volume. I'm assuming you're in a pipe run in a processing plant or a gas pipeline. The amount of water that you're going to have to be used is relative to the volume of and the amount of surface area that you're going to treat. And the circulation loop. I mean, you can design your circulation loops to be large or small, but they're each unique to the characteristics of the facility.
Yep, fair point. point. Very good point. Yeah, thanks. So last one. You've done great. You've survived right through till the end on these. And thank you everybody as well for all these great questions. I wish I understood at least half of them. So is there a potential for the nitrogen flushing technology to be progressed for use in subsea pipes in situ?
Yeah, of course we considered that. That was of interest to us. The problem with subsea pipes is that so the nitrogen flushing really, just pure nitrogen is not going to do much for you. It's got to be hot. And so the dry decon system that I've shown you is really based on the thermal energy that's put into the pipe to drive the pipe temperature up to 600 degrees centigrade. For subsea applications, the difficulty is the access. Now I can imagine it would be difficult to deploy something like this in subsea pipe. And you know, the water temperature and the pipe temperature at subsea depths it gives a lot of cooling. So
yeah, you need a lot of energy to heat the pipes to those temperatures.
Yeah.
Oh wow. Well, you've done remarkably well there, Vic, for this time of the afternoon, for you to field so many questions there. Thank you very much for bearing with me as I tried to fumble my way through questions that were way beyond my own personal knowledge as well. That has been absolutely brilliant. Thank you so much. And thank you everybody for joining and staying with us for this webinar. We will be putting a recording of this webinar up on our YouTube channel in the next few days, probably early next week. I would expect it'll be up there. They'll be sort of be available for people to watch, share with your family. You can go back and watch it, James, and torture yourself over things that you may have said differently that you would have said otherwise.
I'm sure my partners will do that for me.
Oh yes, I noticed there was a bunch of them on this call, so they've probably got a whole bunch of questions for you now when you finish.
Can't wait to see them tomorrow.
I'll bet. But look, seriously, this has been absolutely fascinating. I mean, it's clear from the numbers that we've had on the call that this is a very, very topical and popular topic. We will make sure that we include all of your contact details in anything that goes out on this, and I'm sure there will be follow-up questions heading to your mailbox or Patrick's mailbox or one of your other partners' mailboxes in the very near future. So, look, on that, I'll close it. Again, thank you everybody for joining us for this one, and watch out for future webinars as the year rolls out. So thank you, and have a great whatever rest of your day is.
Thank you, Francis, and thank you everyone who attended.